Welcome to Elementary Algebra, Chapter 17, Number Sequences. The author is Harold Jacobs. I'm your presenter, Molly Crocker. This material is copyrighted. Chapter 17, Lesson 4, Infinite Geometric Sequences. What we have today is a special category of geometric sequences. Did you read the lesson? If not, then pause the video here. I'll be back in 5 seconds. For the category of geometric sequence we're looking at, the ratio is close to 0. It could be positive or negative, so we can say the ratio is between 0 and 1 or between 0 and negative 1. And the terms will approach a number. Let's have a look at that. A way to say this, where the ratio is a way to abbreviate it is to write it using an expression in absolute value like this. The distance of the ratio from 0 is less than 1. The formula for the nth term of a sequence is the same as any geometric sequence. Let's look at what happens when the ratio is positive. Here's the formula for the nth term. Pick a first term, I picked 3 in this case, and see what happens to the sequence. Oh, by the way, I picked a ratio of 7/10. I'm going to use the function mode on my calculator, which means that instead of n, I'm going to use x, the shortcut x button. This equation generates this table, and the graph of that as a bar graph will look like this. Now, you should be able, you should pause the video and catch up and get all this on your calculator and have a look at the table. Your table will be vertical and not horizontal. And your calculator, if you press the graph button, will just show a curve that looks kind of like this bar graph. But the curve is a graph of a function, not a sequence. Let's do the exact same thing, but this time r will be negative. Negative 7/10 instead of positive 7/10. Here's the table. And the bars in the chart alternate between being above and below the x-axis. Why? Term 1 was positive, and when that is multiplied to a negative ratio, the second term becomes negative. Then a negative multiplied to a negative is positive, and so forth. Let's review what we have so far. This is about geometric sequences. If the ratio between terms is greater than 1, then we will have ever increasing values. But if the ratio is between 0 and 1, we will have ever decreasing values. If the ratio is less than 1, then the values in the sequence will alternate between being positive and negative, which makes the bars in the graph alternate between being above and below the x-axis. And they will get farther away from the x-axis. Finally, if the ratio is between negative 1 and 0, then the values again will alternate between being positive and negative, and they will get closer to 0 out to the right. Now, we have an interesting feature that concerns the sum of the terms in an infinite and diminishing geometric sequence. One more time, did you read the lesson? I'll sympathize with you if you thought it was a lot of alphabet soup. This is tough stuff. So we need to talk. Something interesting happens when we add up the terms of an infinite geometric sequence. Let's do a little exercise. Grab a blank sheet of paper and fold it in half across the long side like this. My image won't look exactly like your paper, but follow along. I'll talk slow so you can do this in real time, but you may need to pause the video and catch up. Label the left side 1/2 like this. If you like, shade in that side with your pencil or a marker. My highlighter happens to be green. Don't be meticulous here. This is a brief demonstration. Now, fold the paper in half across the short sides and label the lower right corner 1/4. And also label it as 1/2 raised to the second power as shown. And shade it in. Now fold the right edge of the paper to the middle, but you only need to crease part of it, the upper part of it. And label one of those pieces. And shade it. And now, do you see where we're going with this? Fold the top edge to the middle, but crease just part of it, and label it as shown. And shade it. And you can keep going until this gets ridiculous. 1/32, which is 1/2 to the 5th. And then 1/64, which is 1/2 to the 6th. And now for the grand question. If I had a half of a half of a half added to the half, just keep adding all those halves together, what number does all this cutting in half and adding approach? Well, how much of the paper will we end up covering? One whole sheet of paper. Could it ever equal exactly 1? No, but it's going to get very close to 1. So here's our formula for the sum of terms of a geometric sequence. In our case, our first term was 1/2, and our ratio was always also 1/2. These plug into the formula like this. And then to get it onto our calculator, let's substitute 0.5 for 1/2 and simplify the denominator to -1/2. And then I'm going to go to the next side with the next click, and I will keep this calculator screen up there. And then if we go to the table, we see the sum of terms approaches 1 sheet of paper. Now, if you read the lesson, you'll see something about simplifying this sum of terms equation. Let's go through how that works. First, I'll make the distribution across the numerator t(1). I'll distribute that through the numerator. And then let's consider what happens to the value of this part of the expression when n gets very large. If, for example, r is 1/2, as we just looked at that, then raising 1/2 to a larger and larger power means that the first term multiplied to a tiny number approaches 0. The first term multiplied to a half of a half of a half of a half of a half is going to approach 0. Let's just make that go away, because essentially it becomes 0. Now, you'll notice that n fell out of the equation altogether. We're not talking about n terms of the sequence anymore. We are adding all the terms. Let's simplify this a bit more. If I apply a glorified 1 to this fraction in the form of -1 over -1, then the signs on the top cancel each other out. It's just t(1) on top, and I can reverse the difference on the bottom. If you need to, pause the video and study this process for a moment. This is going to be our formula for the sum of terms of an infinite geometric sequence where the ratio is within 1 of 0. That's not so bad. One more time. This formula applies to the sum of terms of an infinite geometric series where we keep going and going, as in how we added more and more pieces to the sheet of paper, and where the ratio is within 1 of 0. The ratio could be positive or negative. We will indicate the sequence as infinite like this. For example, with the 3 dots in the last position. This is the one in your book. Do you see the dots at the end? If you do not see the dots at the end, or if you are told that there are 10 terms in the sequence, then you will use the other formula, the one that has n in the exponent on r. By the way, those 3 dots are called an ellipsis. In writing, it means an incomplete thought or a sentence that didn't get finished. In math, it also means an incomplete thought, or that the reader should be seeing a pattern so that the author doesn't have to write it all out. We can be lazy mathematicians. Now, an interesting application for the infinite geometric series is the conversion of a repeating decimal to the quotient of 2 integers. This is version 2 of that process. We learned one version back in chapter 11. Here's the other. In the book, there were 2 decimals that repeated. I'm going to do a shorter one for the sake of space on my slide. If a single digit, say 6, repeats, then 0.6 repeating means 6/10 plus 6/100 plus 6/1000, etc. I've also presented that as the sum of fractions. Then we see the first term is 6/10, and the ratio between the terms is 1/10. I keep multiplying by 1/10 and I get the next fraction. Let's plug this all into the formula. Now, in the denominator, 1 minus 1/10 is 9/10, and we have a fraction divided by a fraction. So let's flip the denominator and multiply, that's the part in red, and making a glorified 1 out of that flip. That's what's in red. Now, discarding the glorified 1s, there's going to be cancellations that are made on the top and cancellations made on the bottom. We have just 6/9, which simplifies to 2/3. In problem 4, let's talk about the homework. In problem 4, you're asked to find the ratio between terms. This is done by dividing any term by the one before it. Don't try to start this with the first term. Start with the second term or a later term and divide by the term in front of it. In problem 5, try to make the connection between the size of the ratio and what happens with the size of the subsequent terms. Refer back to slide 6 if you need a reminder here. Problem 9. I'm hoping you remember the Pythagorean theorem so you can find the length of the hypotenuse of the triangles in the corners. A squared plus B squared equals C squared. Leave your answer in simple radical form. Then use that expression in the Pythagorean theorem again to find the side of the next smaller triangle. Problem 10. You're going to be adding up all the heights of the bounces of the ball in this problem, and for all intents and purposes, the sum of those heights is the sum of the terms of a diminishing geometric series. That's your clue. Let's summarize this chapter. This lesson. For an infinite geometric sequence where the ratio is between -1 and +1, the formula for the nth term is the same. The graph will approach 0. If r, the ratio, is negative, the bars in the graph will alternate sides of the x-axis. The sum of all the terms will approach a number. The formula for the sum of terms of an infinite geometric sequence with the ratio, the absolute value of the ratio less than 1, or the ratio between -1 and 1, is the sum of the terms is equal to a fraction. On the top is the first term. On the bottom is 1, take away the ratio. An infinite geometric sequence can be used to find the fraction that is equivalent to a repeating decimal. Yes, that question is going to be on the test. That's all for now.